we look at a lot of really standard surfaces, things like spheres, we look at paraboloids, we'll look at hyperboloids, and I guess there's another kind of hyperboloid that has two sheets like this. And then you have ellipsoids that are like oblong spheres and things like that. These are kind of standard, and they're kind of interesting, but it gets really a lot more interesting than just these guys. No matter what surface you're dealing with, no matter what equation relating x, y, and z, you should always look at these z equal constant slices, these y equal constant slices, and these x equal constant slices, and try and piece together what it all looks like. So I've given us another example here, something that's a little bit more intriguing. Let's look at the equation that's described by z equal to cos x times sine y. Okay? Now, first of all, I want to kind of highlight some of the interesting things that we can see here. For instance, notice that when we set y equal to 0, when we look at a plane, I guess that looks like this one right here, that's kind of coming out of the page at you. You plug in y equals 0, what is sine of 0? Sine of 0 is just 0. So if you plug that into the formula, you're going to get z equal to 0. So that's going to be this kind of point of this line of flatness there. And in general, actually, that's not the only time sine of y is going to be 0, is it? Sine of, I guess, pi, if we're using radians, or 180 degrees if you like. That too will lead to sine being 0 and z equals 0. And same with, 2 pi and things like that. So 3 pi, 4 pi, really any integer multiple of pi would work. That's not the only time z equals 0. What if we get cosine of x to equal 0? So when you look at these x slices, these kind of slices like this, well, if you plugged in not x equals 0, but I guess x equal to pi halves radians, or 3 pi half radians, or things like that. That's all places where cosine are 0. Quick trigonometry review. There's your unit circle. Remember, pi halves is here, which has x coordinate 0. 3 pi halves is there. So that's how I knew cosine would be 0 at values like this. Really, we're looking at top and bottom of the unit circle. So again, those are going to lead to z being equal to 0, these kind of flat places. If you fix z, you're going to have this really weird, you're going to take this horizontal slice of this weird shape given by this equation, and it's going to be given by something like, well, if this is 1, then if z equals 1, that's the z equal to 1 space, then that's going to look like cos x equals 1 over sine y. What on earth does that look like? Well, we'll see in a moment when it gets graphed. But then you'll also ask ourselves questions like, well, what happens if I fix x? Well, if I fix x at some value that doesn't make cos x 0, then that's just some kind of arbitrary constant. And then z is, if I call that constant a, z would be of the form a sine y, which looks like a sinusoid. Something like a sine curve between the z and the y. So again, fixing x means fixing this thing. So I'm saying that the cut should look something like that or something like this. So without further ado, I'm making it sound very interesting. Let's actually look at it. See what this crazy looking surface looks like. Alright, so you guys can start to see it. Let's zoom in and see what it is. Alright, that's actually a really interesting looking surface. Right, so you can see that it has these sinusoids trapped in. Let's add to the mix, say x equal to 1 or something like that. And then regraph it. I'll zoom out. You have to kind of zoom out in order to see all of this. That's very bizarre. I'm not sure why it lost track. Maybe I should be zooming in instead of zooming out. No, it seems like I shouldn't. That's unfortunate. Oh, wait. I can start to see it. Rippling up. That's very bizarre. Let me see if I can get rid of this formula here. z equal to 1 here. I don't want any of that. Let's regraph these things. Okay, there we go. There's our little surface again. So there it is, even more zoomed out. Looks like that little ripple thing. But you saw what I was trying to do. I'm not really sure why that didn't work. It must be some kind of problem with the program that I'm using here. But I just wanted to show you what these various cuts would look like. And you can imagine what it would look like if I cut it. Let's just try one more time. Let's see, I cut it with something like z equal to 1 or something like that. And hopefully when I graph it, it looks like something. It won't zoom out. Wait, I think it's doing something. No, apparently not. Oh, I can start to see ripples now as I zoom out, but then I lose the ripples. So this is not a very good idea, but at least you got to see one complicated looking surface that was actually very interesting looking. And we did talk about, unfortunately I can't show you the intersections with planes, but we did talk about what these sorts of things should look like to an extent. But the whole moral of this video was just to say it doesn't have to be these kind of standard stock shapes that we're looking at. There are a lot more interesting surfaces you can look at, and the idea of slicing them to see what they look like is going to apply no matter what surface we're talking about.